kind of a surprising result that we get from this is if we take a look at the fraction of molecules that are in the jth rotational state based on a thermodynamic partition function. And let's take a look at that. What I'd like to compute really is what I'm going to call is F sub j, which is the number of particles that is in the jth state divided by the total number of particles. That's really just the probability. Look at it, that the jth state. But I'll think of these now as the fraction that's there. And we know what that is in terms of the energies. It's just the E rotational energy divided by kBt, which we've written in this form, J times J plus 1. And then the degeneracy of those rigid rotator energy levels divided by the Z rotation. And we've got all those things. Yeah? The degeneracy, I gave that earlier, was 2J plus 1. And we have our Boltzmann factor. And then, of course, we have to divide that by our partition function. Again, I'm looking at the case where sigma is the symmetry number is 1 here. So if we had a gas that had sigma is 2, a homoatomic gas, then a diatomic gas, then they would have a factor of 2 here. So, but here we're looking at just the case of a heteroatomic molecule. Well, I can simplify a little bit. The theta flips over on top in T. And what I'd like to do is use that. This is the fraction of all the molecules that are in the jth state. And I'd like to find the most probable value. So I'd like to find the J value that has the most likely has the most particles in it. Right? And that's the maximum value. And I know how to maximize any function. Here I've got a function. I just need to maximize that and maximize it with respect to theta. In our system, theta rotation is a constant, T is a constant. So my variable is J to get this F of J. And I simply have to maximize it, find where its derivative vanishes. So to find a maximum, so we just use a little bit of calculus. One can differentiate this with respect to J. The easy one is this one. I just picked up a factor of 2 times everything else that's there when I differentiate this term in parentheses. And then I need to differentiate this this exponential because it has a J in it as well. If I do that, what I get is the exponential back again times the derivative of its argument up here. And that'll pick up a minus theta rotation over T, which will combine with this one, so it gets squared. And then I'll pick up a factor of, when I differentiate this argument, J squared plus J, I'll pick up another factor of 2J plus 1, so that term here then becomes squared. So just take the derivative with respect to J of this expression, and I think you'll find that you get this. I set that equal to 0 to find the J value that's where the maximum occurs. You get some cancellation. The exponential factors go out. One of these powers here will cancel one here. And so this term, everything has gone out, is just get a factor of 2. You get a 2J plus 1 squared. And one of these is canceled out from this one here. And so this is just theta rotation over T. And now then I solve that for J. So I solve it for J. What did I do? I brought the 2 over to this side and then multiplied through by T theta divided by theta rotation. I took the square root of both sides. That gets me down to this. Then I divided by 2, it looks like. And then finally took the 1/2 over to the other side. And so that gives me the value of j equal to this. Remember, I took this 2 inside here, so that as I take it underneath the square root, it becomes 2 squared, and so it'll cancel. And that's the j that's equal to j max, where the maximum occurs, and that's the value of j where the maximum occurs. And in general, it's not 0. Some value bigger than 0. If I were to plot, fj for j equals 0, j equal 1, j equal 2, you would get something like this. It's going to come up, rise to a peak, and then decrease again. It's actually discrete, so you'd start having a discrete, so you really just get points. But the maximum value, the place where the j angular momentum quantum number, where you get the most particles, most of the oscillators in that state, is not 0. So kind of a surprising result. The most probable state in these rotational systems is not the j equal to 0. And that's surprising because generally nature is such that it likes to be at minimum energy. And the minimum energy for an oscillator does in fact occur at, I'm sorry, the maximum is they're all going to pile into the lowest energy, which occurs at j equals 0. So this is a kind of a surprising result, that you'll get a distribution in terms of j, and in general, most of the particles will not be in the j equals 0 state of these rigid quantum mechanical rotators.